In the previous videos, we were talking a lot about a picture like this, in which we have what we call a comprehensive study. So think, for example, that we are studying surgical procedures and we are interested in the days to recover of patients. So we had over here the inputs, let's say those are the patients, and we're interested in their recovery time. We were interested in seeing what is the effect of some controllable factors, let's say their surgical procedure, on the recovery time. And we talked about factors that we can control, such as what procedure we employ or which procedure we use, maybe the surgeon, and maybe the equipment. But there are things that we cannot control. Still, we can measure them, but we have no control over them, such as the sex of the person, the age, etc. And we also saw that there are unknown factors, things that might have an effect on the response, on the recovery time, for example, but we have no idea about, or we do know about, but just don't have the ability to measure that. So it could be, for example, some previous conditions, things like that. And so the ultimate question all along is, what is the effect of the factors of interest on the response while controlling for all the other factors, all the other effects? So now we're going to build a model of this process to try and better understand how this works and maybe make predictions, find out what exactly is the relationship between the factors and the response, etc. So it's all about building a model of reality, or putting on the one hand the model and on the other hand the reality. In reality, that phenomena we want to study, our object of study, works something like this. There is some process, again, artificial or natural, we don't know. And that process depends on the variables we know about, but also on the variables we don't know about. So it depends on the X that we know and the X's that we don't know. Those are the ones that ultimately determine the response, the Y. Now, we don't have full knowledge of the process. That's the point. We're trying to understand it. Still, we have no idea, perhaps. We maybe know a little bit or have some intuition as to how it works. The point is, we can still make a model about it, build some function f, given the observed variables, given only the x's we know about. So we could think about building this function, this f, given the things we know, the things we are able to measure, and from there try to understand why. And of course, because we don't have full knowledge of how the process works, we don't have full knowledge of all the variables involved in that process, we're going to have some error, let's say epsilon. This epsilon represents two things. First of all, the fact that the model is different from the process. Those are two different things. And the other one is that we have no knowledge of the unknown. So we're trying to make a model of the y based on only part of the things that determine y. Still, that might be useful. Everything is under the assumption of some class of models, capital F. So we calculate some estimated model, so some f hat, from the family that is somehow useful for us. So we're going to see about making a certain assumption about what the model looks like, and then it's about having different data, fitting a model or estimating a model, some f hat, that allows us to study the relationship between the x's and the y. And so the classes of models are just a set of possible models or a definition of what the model looks like. It's just a set of all models with a certain characteristic. So let's say we could say a class of models, we call it F1. It's all linear models that have the following form. So we say the response y is some kind of constant, beta 0, plus a constant times the first variable, plus a constant times the second variable. So this is all the linear models with two variables, x1 and x2. Maybe we are interested in another class of models, let's say f2, and it looks something like this. So it's a constant times x to the power of b plus another constant. So the coefficients here are a, b, and c. These are the parameters of the model, and we only have one independent variable, which is the x. So given the class of models, a model from the class is just one specific instantiation of the model. So for example, if we have this one here, y equals 2 plus 4 times x1 minus 1.3 times x2, this is an instance from f1, in which beta 0 equal 2, beta 1 equal 4, and beta 2 equal negative 1.3. If we have the model y equal negative 0.9 minus 2.21 x1 plus 0.43 x2, or whatever numbers, this is again an instance from the first class of models. Over here we have an instance of the second class of models, etc. So you can think about it as a specific instantiation of those coefficients in the model. So if we talk back about models versus reality, let's assume we are studying some reality that looks something like that. Of course, we have no idea about this picture, what reality is about, but just for illustration, let's pretend it's something like this. So we know that the dependent variable y depends on two independent variables, x1, which seems to be numerical, and x2, which seems to be categorical. It relates to two groups, A and B. And so they have this quadratic relationship over here. If we are a member of A, according to variable x2, then the relationship is 2 plus 1.5 times x squared. And if we are a member of group B, then we have 50 plus 1.5 times x1 squared. So the relationship looks something like this. Now, we want to build a model of this relationship. The first thing we have to do is make an assumption or a best guess about the class of models. So let's say, hey, we only have knowledge about x1. We have no idea about x2. So our class of models is going to have only one independent variable. Let's say we assume a linear model. So our class of models, the capital F, is beta 0 plus beta 1 times x1. So we only have knowledge about one variable, and this is the relationship with y. So our model looks something like this. And so this epsilon, again, captures two things. First of all, that reality, the real model, is not in the class of models, because the relationship we have in reality is quadratic, and the relationship we have in our model is linear. There's no x1 squared. And the second one is that we have no knowledge about x2. So it's impossible that we have a model that looks like reality, because we're missing one of the variables that determine the response y. And so given this assumption about the class of models we're going to use, we can think about the best model we can possibly think of to model this reality. And that would be something like the black line over here. So the optimal model is something we have to talk about. So let's suppose we observe, again, the output variable y. By the way, we can also refer to it as the response, the dependent variable, the target, or the outcome. And we also have p independent variables, x1 to xp, also known as predictors, independent variables, features, or covariates. Then we assume there is a certain relationship f from the class that is optimal in some way. We will see later on what this optimal really means. So this optimal model relates the x's to the y, and of course there's some degree of error, the epsilon. This is the one that is optimal in a certain way. This is what we are after. So this f models the systematic relationship between the x and the y. It's something that is fixed, but we don't know about. So the black line that we saw earlier. And then epsilon is going to be a random error term, or at least random to us. We will see later exactly what this means. It's something that is independent of x. So in the previous picture, what we have is this line is the systematic relationship between x and y, and then epsilon is going to be giving us this error, or rather than giving us, is going to model this error that we have no idea about or where it comes from. And so statistical learning, it's all about estimating this f, this optimal model. Choose one estimate f hat from the class of models that is the best one in a certain way, or is as close to this optimal model as it can possibly be. Let's see with a little bit more detail. So again, we have here the picture of our reality. Let's say this is the optimal model again. We collect some data. So we actually have 30 observations from this process, some blue points over here, some red points over here for A or B, and we build a model that best describes that data given the class of models. And let's say that that model, that specific estimate of the model is something like that, 0.74 plus 15.23 times x1. Okay, fair enough. Let's say we replicate our study and we have a different 28 observations. They look something like in here. Then, of course, the model is just a little bit different, right? So we have negative 8.82 plus 16.27 times x1. It's quite different if you think about it. Just look at the difference between the first coefficients. Anyway, let's say we replicate again and we have a different 37 observations. They look something like that. This is our model. And we have a fourth data set. We have 37 observations again, but the model is again slightly different. So what's going on? Why do we have all these different models? Well, you guessed it, it's because we have different data. But there are nuances here. So let's say we look at the same reality, but now we're going to make a different assumption as to the class of models. So instead of assuming it's going to be a straight line, what we're going to say now is that there is a quadratic relationship. So now we have beta 0 plus beta 1 times x1 squared. This is a second class of models. Now, under this class of models, the optimal one is the one in black here that you see. It fits the data a little bit better. Still have no idea about the difference between A and B, about the red and the blue, but at least it knows about the quadratic nature of the relationship between y and x1. So let's look back at the data we had earlier. So in the first data set, we had 30 observations, and now the model looks something like this. And I'm just realizing we're missing a square over there. So this is now the relationship, the model. It's quadratic in nature. It's a pretty good fit, I would say, but still has no knowledge about x2. So there's no difference between blue and red. So it just goes kind of through the data points, through the two groups, kind of in the middle. The second model looks something like this, and we see that it's not that much different from the first one as we had earlier. The third model, something like this, and the fourth model, again, something like this. So you see, we can kind of see that the variability across the models is not so high as earlier. Kind of the final model we fit is a little bit closer to what it's supposed to be. Why is this? Well, this has to do with the notion of reducible and irreducible errors. So in our example, we are talking about a y, a dependent variable that is numeric. And we might think about what is the expected error of the model given our observations or across all observations. So if you think about it, we have the true value of the observation, the true value of y, and we have the estimate coming from the model. So we might think about the squared deviation, kind of the squared error of the model, given some specific observation of the independent variables. And we might ask the question, what is the expected such error across observations? So this is actually the expected value of this expression over here. So we have the value of the optimal model and minus the value of the estimated model squared. If we do some math, then it's going to reduce to two different terms, the one in blue and the one in purple. The one in blue, if you think about it, is the difference between the optimal model and the estimated model squared. This is what we call the reducible error. And then we have, again, something about epsilon, something about the error that is always going to be in there. And in particular, we had the variance of that error. So in essence, the magnitude of the error, how much we have. So the reducible error, the part in blue, is something that we can minimize. We can always try and make our estimated model as close to the optimal model as possible by choosing just a different set of coefficients, a different model from the class, or using better predictors. We have this error because generally the one we estimate from data is different from the optimal one. In one way or another, there's going to be a slight deviation because our estimate depends on data. And so this is what statistical learning is about reducing this error or this difference between the optimal model from the class and the model we estimate given some data. But we always have the irreducible error. And this is always going to be in there. It's kind of an upper bound on the quality of the model. And it comes from the fact that even the optimal model is different from the real process, is different from reality. And also we have the unknowns, the unknown variables. So in our previous example, we don't have knowledge of x2. And so regardless of what kind of magic we play with x1, it's going to be impossible to get the real model because we don't have anything about x2. And this is why the study design is important. This is why all the previous lectures about how we properly design a study are important, because unless we have knowledge and observations about everything that can potentially affect the response, we're always going to have a irreducible error. It's always going to be in there, regardless of what fancy models we build. Always going to be an irreducible error in there. We have to minimize it by having a better design. And so in the previous example, again, we are going to be able to reduce error here. The reducible error is going to be smaller in this case than in the linear case because we are closer to reality, yes, in terms of x1, but there's always going to be this difference between the blues and the reds and the estimated model because we have no knowledge of x2. This is an error that is irreducible, it's always going to be in there. So at some point, we have to say that all models are wrong, but some are useful. Of course, all models are wrong, all of them, because they're based on assumptions about variables, about the structure of the model, about how variables relate to each other. We don't have knowledge of all the variables that affect the response. All models are wrong. Still, some of them are going to be useful because they're going to allow us to better understand what's going on, better understand how a specific relationship looks like. They're going to allow us to test specific hypotheses, make predictions, etc. All of them are wrong. The point is, are they still useful for us? And they're going to be useful for normally one of two things, either to make predictions or to understand the object of study. So if we're interested in predictions, we want to estimate the function or the model to make predictions, then it's something like this. We are going to try and find the f hat that, given some new data, some new x's, is going to allow us to estimate the dependent variable, the outcome. And so this model is typically seen as a black box. Black box in the sense that we don't really care about how it looks like or what's inside, what's the relationship between the variables. We only care about the accuracy, about how well it makes these predictions. That's it. How complex the model is, what's inside, we don't really care. We only care about whether it makes good predictions. And then there are objective and well-defined measures of how good the model is. So how do we evaluate, how do we tell whether the model is good or not, or how good it is? And then the point is we try to optimize those different criteria when we choose a model. We'll talk plenty about this. Now, the other option might be, hey, we are building a model to better understand reality. And so better understand the relationship between the independent and the dependent. And so in this case, the model is seen not as a black box, but as a glass box, something that we want to see through. We do care about how it looks like, what's inside, what's the shape of the relationships, because we want to understand precisely how the x's relate to the y. We don't care so much about the accuracy of the estimates or the predictions from the model. To some degree we do, but the most important part is we want to be able to understand, to open the box, take a look inside, and then gather some new insights about reality based on what the model is telling us. And this is going to be very useful for explorative data analysis because it will allow us to think in terms of what predictors are associated with the response, what x's seem to have an effect on the response, which are the most important, and how is the relationship between the variables, that kind of thing. And so depending on our goal, whether we want to predict something about new data or try to understand how the different variables relate to each other, we're going to use quite different techniques to estimate the model. So for prediction, we very rarely care about the model complexity. Lately, we have some research and a lot of interest in trying to explain why the model makes a certain prediction. What are the factors determining that a model makes a yes or a no prediction, for example? and making sure that the model is fair, that it's not biased against certain groups of people, for example. And when we talk about understanding, then we tend to use a simpler model because it's easier to understand, it's easier to explore, to take a look at, see what the relationship among the variables is. Now, in this course, we're going to pay more attention to the simple models because we have a stronger emphasis on understanding, on designing a study to properly understand some object of study. And so we're going to have quick mentions to more complex models or classes of models, families of models, but we're going to focus on the simple ones because they're going to allow us to better understand reality.